All right. Hello and welcome everybody to another physics video lecture. Today we're going to be talking about wave behavior, right? So the past couple of classes, we've looked at the types of waves, we have looked at the different parts of those waves, and we've looked at all the equations to find their wavelength and amplitude and frequency and period and velocity, all that stuff. Today we're going to be looking at how those waves work in the real world, all right? So the first thing you have to understand is that when we're talking about these behaviors happen to all waves. So we're talking water waves, waves on a vibrating string, my personal favorite, the old slinky. We're also talking about sound waves and light waves. Any type of wave, it does these three things, or these four things. And the four things we're going to look at are reflection, refraction, diffraction, and interference. Okay? So let's jump in. So the first thing we're going to talk about is reflection, and this is something that I'm sure everybody is familiar with. You probably, you probably already knew what this was, right? So reflection is what happens when a wave hits a barrier and then bounces off. What's a barrier? A barrier is anything that you can't go through, okay? So it's a solid surface, right? Now, whenever any wave hits that, it's going to bounce off of it. And I'm sure you're used to this, seeing light bounce off of a mirror. And that's a great example, okay? Or here, we see the light bouncing off of this super clear lake, right? And seeing the beautiful picture of this mountain, okay? Now here is a very good diagram of what we call the law of reflection, all right? But before we get into that, let me talk about some other ways that reflection actually happens in the real world, right? Now, here's the law of reflection. You're used to sound waves reflecting, light waves reflecting, but you have to realize that sound waves also reflect, okay? This is something that is called sonar, all right? And it's something that a lot of animals use, and it's something that we as humans have actually borrowed and used for ourselves. And one of the animals that uses sonar to actually fly around are bats, okay? Not all bats are blind, but many of them have horrible vision, and the way that they actually see things is that when they're flying around, they will emit these really high-pitched little shrieks, and they have this system where their ears are so big that they can hear that sound go out, and depending on how much time it takes to come back, they can tell how far away something is from them, which is amazing, because if you've ever seen a bat fly, they're all over the place, and they can catch bugs out of the air doing this. It's incredible. Dolphins use it. I'm sure there's other animals that use it too. We have borrowed this and used sonar in our boats, right? And this is actually how we are able to tell how deep down something in the water is. And it's a pretty simple system. You send out a sound wave, that sound wave goes down, it bounces off of the surface and it comes back. And depending on how much time it takes to go down and come back, you can tell how far away something is. And if you've ever been on a fishing boat that has like really advanced technology, you may have seen these like fish scanners, and that's all that is. It's just, thousands of sound waves going down and bouncing up and giving us a picture of what we see. If you're into comic books, this is actually how Daredevil sees. He's blind, but he uses sonar, which is pretty cool, okay? All right, so to look at this law of reflection, I'm sorry, I'm getting ahead of myself. Again, there's two types of reflection, all right? There's what is called specular reflection and what is called diffuse reflection. And it should be pretty obvious what the difference between the two is from the pictures, right? Specular reflection is what happens when a wave hits a super smooth surface, okay? Like a mirror or a super flat body of water, or even just, this whiteboard, okay? What happens is the waves come down, and again, if you're talking about a light wave, there's millions upon millions of light waves. When they hit, okay, since the surface is even, all of the waves bounce off exactly as they came down. This is why you can see your reflection in something that is really smooth, whether it's a mirror or a body of water or whatever, okay? Diffuse reflection. If you ever heard the word diffuse before, diffuse means to spread. A diffuser spreads things, right? So this is what happens when light or sound or anything else hits something that has a lot of cracks and an uneven surface. The waves come down and they hit it, but when they bounce off in a bunch of different directions, okay? So this is like when you see something like a tree. You can't see your reflection in a tree because the tree is rough, and when the light waves bounce off of it, it doesn't work as well. The same thing is true for sound waves and echoes and things like that. That's why if you're in an empty room, you hear an echo really well. It's because, it bounces off really well. Now, we can talk about the law of reflection. And this is a super easy law, okay? All it says is that you have to understand that we have what is called incident ray, which means the starting ray, like an incident is where something starts. And then we have the reflected ray. So here, this is our surface on the bottom right here. You could think of this as like a body of water or a mirror. It works whether or not it's horizontal or vertical or any angle. But what you have to do is from the surface, you have to draw what's called the normal line off of it. And it's just a straight line out, 90 degrees, okay? If it was a mirror going up like this, the normal line would go out horizontal, right? And you have to understand that the angle of incidence, okay, which we draw between the wave and the normal line, that's why that normal line is important. This angle right here, the angle of incidence, is equal to this angle right here, which is the angle of reflection, okay? And this is true from anything that bounces off of something. If you like playing pool, this is how you actually judge your pool shots. Whatever angle the ball hits the wall, it's gonna bounce off with that same angle. And the trick here is to remember that when you measure the angle, there's a reason why we draw this imaginary line. That's because we measure the angle of incidence and the angle of reflection to this imaginary line. So if you see questions about this, that's a big thing to remember. We don't really care about these angles here. Although, you should remember, okay, that this angle is always 90 degrees, and so is this one. So if it gives you something and says, oh, this angle is 60 degrees, what's this angle right here? That's a great question. You'll see this a lot. You'll probably see this on your test. The way that you solve this is you have to go, okay, well, I know that this angle with the surface is 60 degrees, and I know that these two added together have to be 90, so 90 minus 60 is 30, okay? And if this angle is 30 degrees, then this angle has to be 30 degrees. Easy peasy. And this one's 60 degrees, okay? Add them all up, you get 180. So again, the angle, the law of reflection is not super difficult. It's an easy one to see. And again, if you like bouncing things, it's a very useful one to remember. So remember this the next time you're playing a game of pool. Draw yourself kind of an imaginary line with your mind and understand that the ball is going to bounce off the bumper at whatever angle it bounced into it with. All right, up next is refraction, okay? Refraction is what happens to a wave as it moves from one medium to another medium. Now remember, a medium is what a wave travels through, okay? So what do we mean when it changes mediums? Well, let's say a light wave is traveling through the air and it hits the water. I'm sure you've seen this before. What happens when that happens? Well, I'm sure you've seen a straw look like it bends in the water. The straw isn't bending. What's happening is that when the light goes from the air into the water, it slows down. So it looks like it's bending. Usually when we're in class, we do this thing called the Jello Lab, and we take these they're lasers, they're really just flashlights. But we shine them into a piece of Jello, and you can see that as the light's going through the air, it's going fast, and then it bends as it goes through the solid piece of Jello, and then it bends again when it comes out. This is a really cool law, okay? Same thing, this is why shallow water looks light blue, and why deeper water looks dark blue. So when you look in the middle of the ocean, it's darker than when you're at the beach. That's because the water is more shallow, okay? It's just light bending. Pretty cool. Now, what you have to understand about refraction is which way it bends. So, if the light is going from a less dense medium into a more dense medium, and I know more dense isn't a word, but I just like to say it so you can see less and more, okay? what it does, okay, so the example here is light going from the air into the water. So here we have the air, here we have the water. The light wave is going from the air into the water. Now, the way that this wave, this light wave, would have gone is it would have gone along this dotted line. That's what it says right here. But it doesn't do that. What it does is it slows down, okay? And it doesn't travel as fast. Why? Well, we'll get into that, but that's because there's more atoms in its way, okay? Light travels fastest when there's no atoms getting in its way, all right? So what happens is the light wave slows down and it bends towards the normal line. And again, the normal line is always, you guessed it, 90 degrees to the surface. It's this imaginary line that is super important when it comes to waves, right? So again, when we go from a less dense medium, a faster medium like air, into a slower, thicker, more dense medium where those atoms are closer together, the light wave slows down and goes towards the normal line. Okay. Similarly, when a light wave goes from a more dense medium into a less dense medium, okay, for example, if that same light wave goes out of the water into the air, okay, it's going to speed up, right? Because it's going through this thick medium and then pew! It speeds up because there's less atoms in its way. In this case, because it speeds up, it does the opposite and it bends away from the normal line. Again, the normal line is 90 degrees from the surface, and the actual light is going to bend away from that normal line because now it's going faster. Pretty cool, right? All right, number 3 on the list, diffraction. Diffraction is what happens when a wave either travels through a very, very, very small opening or when it goes around a corner, okay? Whenever this happens, the light wave is going to bend. Now, the big difference here, because you're like, but Mr. Norris, it bent in refraction. The difference here is that in refraction, it bends because it changes mediums, okay? It goes from air into water, or water to air, or a solid to a gas, whatever it is, okay? The reason that diffraction happens is because it goes through or around something solid, something that's physically there. Now this may sound weird, but it's perfectly easy to understand, okay? Think about if you had the ocean or any water and you had a small break in the wall stopping that water from coming through, right? When the water comes through the wall, for example, picture the room I'm in. If water was outside of the room and it came flooding in through the door, the water wouldn't just go straight into the door, right? Not at all. As I'm sure you're aware, if that water came through the door, it would do exactly what you're seeing here, and it would spread out like this, right? That is exactly what we see, and that is diffraction. Okay? Here's kind of the overhead view. Again, we have these straight waves, think of water waves here, and they hit a surface, and there's a little tiny hole in that surface. As the water comes out, these waves are no longer straight, but now they bend, and they spread out. Okay? Pretty cool, right? Again, the other example here is when waves go around a corner. As I'm sure you're aware, when you walk around a corner, you can still hear what's going on. This is why you're able to hear what happens in another room, right? Or if you're standing on one side of a corner, you can still hear the radio on the other side of the corner. That is because the waves are able to spread around that corner, okay? This is also why noises in a big city get lost because there's buildings and cars and people. And as those waves bend, they slow down, right? Friction. But if you're in a very open place, like if you're on a boat in a lake, sound travels super far. Why? Because there's nothing to stop it. There's nothing to slow it down. Diffraction. Good stuff. All right. Lastly, interference. Okay. Now, if you're a fan of sports, You know that interference is when one player messes with another player. And that's the same thing that's happening here, okay? Interference is what happens when two waves hit each other, okay? Now, when two waves hit each other, one of two things can happen. The first we're going to talk about is constructive interference. Now, when you hear the word constructive, I'm sure you think of building. This is what happens when you build something up, okay? And constructive interference is what happens when two waves hit each other and they make a bigger wave, okay? Now, the fancy way to say this is that two waves come together, okay, and they superimpose. What that means is they come together and they add on top of each other, all right? They add together. Now, what we call this is in phase. This means that the two waves are in phase with each other. And the reason the way you can tell the two waves are in phase is because their crests line up and their troughs line up. Does everybody see that? These two waves are in phase. The crest of this wave lines up with the crest of this wave. The trough of this wave lines up with the trough of this wave. And what that does is when you add these two waves together, you get a much bigger wave, okay? And you see that here. Whenever you throw two rocks into a pond, when those waves line up, okay, you can get a much bigger wave. My favorite example of this, if you've ever been on a trampoline with a friend, and if you can synchronize your jumps, okay, you can end up making each other go way higher. That's because the waves you're making are in phase, and they make bigger waves, right? And there's a lot of examples of constructive interference, okay? For example, amplifiers, speakers. If you can get two speakers in phase with each other, meaning that again, their crests line up, it just means that the waves line up, that they superimpose, which means they go over each other perfectly. You get a bigger wave. Same thing happens with light. You can see it right here. Here's two lights coming together, and when the two lights come together, they make an even brighter light where they hit each other, okay? They're coming together and constructing a bigger wave. They're interfering with each other, okay? Not a bad thing, it's just what's happening. Now, if we have constructive interference, the opposite of constructive is destructive, okay? And I'm sure you know what that means. This means to destroy, to tear down, okay? This is what happens when two waves come together, okay, like this, and cancel each other out, okay? We say that the waves are out of phase, okay? They're not in phase with each other. And again, all that means, look closely here at the difference. It means that the crest of one wave lines up with the trough of another wave, and that its trough lines up with this wave's crest. They are perfectly out of balance with each other. So when they hit each other, the crest of one wave hits the trough of another, and whoosh, they cancel each other out. Now, the best example of destructive interference are noise-canceling headphones. The way these work, okay, is that they actually have little recorders inside of them, right? So the reason that noise-canceling headphones, the real ones, right, are so expensive is they have to have these little recorders. And what they do is they record the sounds of everything around you, and they immediately take that sound and they go whoosh, and they just move the wavelength just far enough, okay, for it to be out of phase with everything around you, and boom, you don't hear anything, okay? That's how noise-canceling headphones work. They take the sound that you're hearing, and within like a nanosecond, they just move it like this, so that the crest of the wave of what you're hearing is bouncing off of the trough, and by doing that, you don't hear anything around you, which is super, super cool. To go back to the trampoline example, when you're jumping on the trampoline, okay, if you miss and you end up being out of phase with your friend, both of you guys go and fall flat. And that's exactly what happened, okay? Instead of getting a bigger wave, you get no wave at all, okay? Pretty cool, right? So again, here's just two pictures of the two types. We have constructive interference here. Here, the blue wave and the yellow wave, their crests and troughs line up perfectly, giving us a bigger wave. here, the crest of this wave lines up with the trough of that wave, and you get nothing, flat line. And again, this works for music, this works for light, this works for all sorts of things. All right, so let's look at a couple examples real fast. All right, so here we see this wave and this wave. They're about to hit each other, and because they're both in sync with each other, guess what's going to happen to them? Well, we're going to get A. We're going to get a much bigger wave, because these two waves are going to come together, and they're going to make a bigger wave. Now here, okay, because we have this wave going up and this wave going down, when they hit each other, okay, they're going to be out of phase. And this one's a little harder to see, but if you count them, this one goes up 1, 2 squares, and this one goes down 1, 2, 3 squares. So what you're actually going to end up with is you're going to end up with D. Should I give you a second for that one? Sorry. Because you're going to end up with this bump being 1 square, because you got 2 squares up and you got 3 squares down. You're going to subtract them because they're out of phase, so you get this. Now that you know that, what do you think you're going to get here? Take a second, A, B, C, or D. Got an answer? Okay, good. You should recognize that the waves are out of phase. This one's going up, this one's going down. The crest of this wave is going to hit the trough of this wave. And when they do that, you're going to have to subtract these. You're going to have to subtract this from this, and you are going to get B. Pretty cool, right? What about this one? Okay. Pause it. Got an answer? Very good. These waves, the crest of this one lines up with the crest of this one. They're going to be in phase. We're going to add them together. And if you add this wave to this wave, you get A. Good job. Now, I've gone over this. Just to go over a couple examples real fast. Here we see a bat and a dolphin using sound waves to locate their prey. This is an example of, very good, this is reflection. The waves are hitting something and bouncing back, in this case sound waves. What about this? What is this an example of? Here we see light waves going from the air into the water, going from the less dense to the more dense medium and bending. This is refraction. Very good. What about a picture of this radio right here with the sound bending around the corner of the building? Okay. Here, it's bending because it's going around something solid, so it's not refraction, it is diffraction. Very good. Diffraction. Here, we see wave 1 and wave 2 coming together to make a bigger wave because their crests and troughs line up. This is an example of, this is constructive interference. Very good. What about this one? Here, the top of this wave lines up with the bottom of this wave, and the bottom of this wave lines up with the top of this wave. When they hit each other, they cancel each other out because this is, very good, this is destructive interference. Okay? What do we see here? Well, we see these straight water waves going around a corner and bending, and then going through this narrow little opening and bending as they go through that narrow opening. What do we call water or any wave bending because it goes through a narrow opening around a corner? This is diffraction. Very good. Here, we see light waves, particles bouncing off of a super flat surface. You know this. This is reflection, reflection. Very good. It's bouncing. What about this? Here, we see the light waves hitting a denser medium and bending. What do we call this? It probably says it somewhere on here. It is refraction. Very good. And then here, we have these two speakers, or two lights. These are lights. Okay, now when the light waves hit each other, this is super interesting. Some of the waves, when they hit each other, okay, are going to make each other bigger. Some waves make each other smaller. But this is what we call, is that light waves? It's not waves. Anyways, this is interference, and it's actually both. And we'll get into that more in the future, right? When you have bended waves and they hit each other, it actually gets pretty interesting. You get both constructive and destructive interference. Oh, so many examples. Okay, I feel like that's good for today. We'll go over some of these other examples in class. I got a bunch of examples. Hopefully this helps you guys out. You have everything that you need in order to complete your DOL. If you have any questions, as always, just email me or find me at tutoring. Have a good day.